So today we will talk about we'll relate. And that was in last class. What we did was, in some sense, we used this first definition of Pn. Yeah. So which is Pn. We think of it as an plus one minus origin modulo equivalence relation. So all this homogeneous coordinate ring and how it relates to is how algebraic subsets of Pn relates to cone over algebraic subsets of Pn in an plus one, and these ideal correspondence or this Hilbert null-terms, they all come from this first line in our definition. So today we will take a different view. We also know that Pn can be covered using affine spaces using these map phi's. So this we saw when we defined Pn for the first time, right? So phi is a map from An to Pn, which sends an n tuple B1 to Bn to this class, equivalence class of B1 to Bi minus 1, and then Bi to Bn. So at the ith spot, you should have 1, and then you just put Bi's appropriately. Okay. So that is how. This phi is an injective map from An to Pn, and Ui is so you will call Ui as the image of phi in Pn. So one way we decided. So I told you one way one can give topology on Pn is to ensure to say that Ui's are open subsets of Pn, and any closed subset of Pn. So X, a subset of Pn, is closed if and only if X pre-image of X under phi is closed for all I. Zariski closed, that is, in An. Yeah. So we had also defined Zariski topology on Pn using the homogeneous this homogeneous coordinate ring. Yeah. So the closed subsets are given by algebraic subsets of Pn, which are basically zero sets of homogeneous ideals. So today maybe we'll see. Today we'll see that these two definitions are equivalent. So we know that these UIs cover the whole of Pn, because every element of Pn for every element of every point of Pn, let's say A0 to An, one of these AIs has to be non-zero. So you just let's say AI is among A0 to An. So let's say A0 is non-zero, then A0 to An is linear. So say I don't know why I can't write. So okay. Yeah, it looks like it's going to be something is wrong. You know what might be the problem? I'm not able to write on this one note. Okay. Let me try to restart this and see if this works. Yeah, it's working. So A0 to AN is some point in Pn. Then of course, we know that some AI has to be non-zero. So let's say, say A0 is non-zero, then A0 to AN is same as 1 A1 over A0 to AN over A0. Yeah, because we have this, you multiply by A0 the right hand side, you get the left hand side. Yeah, and since A0 is non-zero, this division makes sense. And this particular point belongs to, I guess, phi 0 of A, which is U0. Yeah. So so every point in Pn is in some UI. So it will be in UI precisely if AI is, so if A0 to AN is in Pn, then this point is in UI precisely if AI belongs to, AI is non-zero. So if all the AIs are non-zero, then of course it belongs to every UI. So it's an intersection of all these open sets. Okay. So, so what we'll see, as I said, we'll see today that X contained in Pn is closed if and only if closed in Zariski topology, closed in Zariski topology, if and only if X intersection Ui um, uh, is closed in Ui. So you think of Ui as same as An, yeah? And then you want to say that X intersection Ui is closed in Ui, again in Zariski topology for AN. Topology for AN. Or I, in other words, phi I inverse of X is closed in AN. Yeah, so this is, we are identifying AI with, UI with AN via the map phi I. Yeah. So saying that X intersection UI is closed in UI is same as saying that phi I inverse X is closed in AN. Yeah, if you identify UI with AN, these two statements are same. So if we prove this, then we would have shown that the Zariski topology on Pn is same as the topology induced by the covered UIs. I equals 1 to I equals 0 to n. Yeah. Okay. So, so that was the other definition of topology on Pn. So this will follow immediately from the following proposition. So we want to say that something is closed if and only if this is closed. X intersection UI is closed in UI. So what does closed mean? That means it has to be an algebraic subset. Closed sets are same as algebraic subsets. So the proposition says that if X is an algebraic subset of Pn, and I, so I is the ideal of X, or you can take I to be any ideal which defines X. Yeah. So you need not take the ideal of definition of X, though I've written that, but it doesn't matter. Yeah. So you take any ideal, homogeneous ideal of Kx not to Xn, such that V of I is X, and let IA be the set fx. So fx not x1 up to xi minus 1, but at ith spot you plug in 1, and then in the other spots you plug in xi plus 1 to xn. Yeah, but you just plug in small so that there is less confusion. Yeah, so instead of capital X, you think of it as small x's. Yeah, for all f in I. So this small f is going to be a polynomial in x naught to xn with x without xi. Yeah, so it's a, so a short way of writing it is x naught to xn with xi hat. So xi hat is missing. Xi is missing. So it's a polynomial ring in n variables, not n plus 1 variables now. Is that clear? Is this notation clear to you? Have you guys seen this notation? Hopefully. So I hope this notation is clear. Yeah. So this precisely means k this is same as k x naught to xi minus 1, xi plus 1 to xn. Yeah, so this is what this notation means. So the pen is acting funny today. Okay. Yeah, this ideal, so this set is going to be an ideal, and the zero locus of this ideal V of IA is same as x intersection ui, or is same as phi inverse of x. If you think of ui as an, then it is same as x intersection ui, or you can think of it as phi inverse of x. Yeah. So anyway, as I said, we'll identify ui with an using the map phi, injective map phi. So phi is a bijective map between an and ui. So we just identify it. So first of all, it's clear that this proposition does our job, yeah. So because if x is closed in, so it does one direction, so one has to do the other direction. So we'll do the other direction as well, yeah. So first of all, it does this direction, that if x is closed in Zariski x is closed in Zariski topology in Pn, then x intersection ui is closed in ui, is a closed subset of ui. And if x is a subset such that x intersection ui is closed in ui, then we also have to show that x is closed in the Zariski topology. So that direction maybe we'll do a little later. Okay, so at least one direction does follow. Yeah? So maybe forward implication is this implication is an immediate consequence of the following. So IA is an ideal is clear, right? Because if you have two elements of IA, so they both look like f of x naught to, so they are polynomials of this form, where little f is in I. So you just take their sum, that will also be in I, and hence it's closed under addition. And similarly, if you have an element, yeah, so f and g are in IA, then there exists f, g in I, such that f equals f evaluated at x naught to xi minus 1, 1, xi plus 1 to xn, and so I didn't give enough space, but okay, and g is g of similar thing, yeah, xi plus 1 to xn. Then of course, then f plus g is f plus g, which again belongs to I, evaluated at similar, yeah, xi minus 1, 1, xi plus 1 to n. Okay, evaluated. Okay, and similarly scalar multiplication. So if f is in kx naught to xn and g is in ia, f is in kx naught to xn with not with xi not there, and g is in ia, then of course G corresponds to some capital G, and F you can make it up. Yeah, so you can write. Um, you can take capital F to be same as small f with x naught replaced by capital X naught and so on. Yeah, there is a more reasonable way of doing it, but in for this for this construction you can just take any the same capital f with just replace x naught little x naught by capital X naught, and then xi don't capital Xi doesn't appear. Okay, so IA is an ideal. Now we have to check that VIA is same as X intersection UI. So let's take an element of VIA. So what is an element of VIA? So A0 to AI minus 1, AI plus 1 to AN, which we denoted by this kind of notation, belongs to VIA if and only if F evaluated at A0 to AI minus 1, 1, AI plus 1 to AN is equal to 0 for all F in I, because IA is made of such polynomials. Yeah, IA is precisely the collection of these kind of polynomials. So for F in I, so this n tuple belongs to VIA if and only if this happens, and this f of a0 a1 ai minus 1 1 f this is equivalent to saying that this is this a0 belongs to ui, because ith component is 1. Yeah, so as I said, if ith component is non-zero, then this then this equivalence class belongs to ui, yeah, as an element of Pn. Yeah, and it of course belongs to S because this n plus 1 tuple vanishes for all F in I. We only have to show it vanishes for all homogeneous F in I, but it actually vanishes for all F in I, and hence this belongs to X intersection UI. And the converse is also true. If this n tuple belongs to X intersection UI, then for all F in I, so for all F homogeneous, this is 0. But but I is a homogeneous ideal, and so that means it's generated by all homogeneous elements of I. Yeah, so if it is 0 for all homogeneous, then it's 0 for all elements of I, because I is generated by homogeneous polynomials. Okay. Any questions? So that completes the proof of this proposition. Yeah. Okay. So so let X be an algebraic subset of Pn. And so I guess we haven't shown the other direction. So I'll show in the process somewhere the other direction as well. Once that step comes, I'll tell you where it has appear. So where the other how the other direction follows. But let's just assume that Zariski topology on X. So we know that if X is an algebraic subset of Pn, and then Zariski topology on X is the topology induced from Pn. Yeah, because that's how we defined. We defined Zariski topology on an algebraic subset to be so closed subsets are those algebraic subsets of Pn which are contained in X. Yeah. So so it's the subspace topology from Pn. Yeah. So so that tells you that since UIs are open in Pn, that tells you that. So why is UI open in Pn? Maybe first we should answer that. Yeah. in the Zariski sense. So how do you think consider UI as a complement of a algebraic subset? UI, so UI is a subset of Pn, yeah. So it should be so to say that it is open in Zariski topology. On Pn we should say that it is complement of a algebraic subset of Pn, yeah. So UI is a complement of which algebraic subset?
Xi equal to 0.
Yeah. So you consider so note UI is open UI is open in Pn since in Zariski topology. Zariski open, I should say. Open in Pn since UI is complement of Xi equals 0. And it's the complement of the 0 locus of the ith Xi being 0. Yeah. So Xi, the ideal generated by Xi is a homogeneous ideal because it's generated by a monomial, yeah, one monomial. So it is homogeneous, and hence V of a 0 set of Xi is a algebraic subset of Pn, and UI is just the complement of this, and hence it's open. Okay. So, since X has the subspace topology, we know that X intersection UIs, UI is an open subset of X, and in fact, since UI cover whole of Pn, X intersection UIs as I vary from 0 to n will cover the whole of X. So this is an open cover of X. And in fact, we know that X intersection UI is affine, yeah, because we proved that X intersection UI is V of IA, yeah. So it is 0 set of some ideal in the affine space. Yeah, so it is an affine algebraic subset. So X intersection UI is an affine open cover of X. Okay, so these are open subsets which are also affine. Any questions so far? Okay. So in fact, as I said, you don't have to take I to be the ideal of definition of X. If X is 0 locus of some homogeneous polynomial F1 to Fm, then X intersection UI, you can get it by taking a dehomogenization. So you take so this IA is called dehomogenization of A, yeah, or this A is for affine, yeah. So so it depends upon which way you want to dehomogenize. So there are many ways to dehomogenize. You can set Xi to be 1. You could have set X0 to be 1, and so on. So there are many ways of dehomogenizing. In fact, n plus 1 ways precisely, depending upon which UI you want to look at. Yeah. So X intersection UI is the 0 set of these polynomials. So it's called dehomogenization because even if when you start with these homogeneous polynomial and you set Xi equals 1, so then it becomes it is no longer homogeneous, yeah. So maybe we'll do one example and it will become clear. Yeah? So consider this F to be this guy, yeah, in Kx not to Xn. So we have already looked at this example, yeah. This is the cone which we saw in last class or last to last class, yeah. And so it is a homogeneous polynomial, So V of F. So today I'm using V instead of Z, yeah, but it's okay, which is same as Z of F, by the way. This is so if you think of it as in A3, then it's a cone. If you think of it in A3, then it is in A3 is a cone. And in P2 you get some curve, yeah, whatever that curve is. So we'll analyze that what it is, yeah. So depending upon which open piece we look at, we'll get different curves. So now so VF is an element is in P2 as well. If you are thinking the zero set in P2, okay. So it looks something, so maybe I'll recall the diagram. So it actually looks like this. If you think of this as, so you draw the real picture. So x2, positive x2 axis, negative x2 axis, doesn't matter. x0, sorry, capital X0. X0 and capital X1. Yeah. So now you want to look at various affine pieces of it. Yeah. So what is U0 so this is our cone. So let's call it C. Yeah, so let's give it a name C. So U0 intersection C. We know is by so by this theorem it says that we have to dehomogenize it in a particular way. So this is so we have to set x0 equals 1. Yeah. So this is U f of so this so f of 1 x1 x2. Yeah. So what is f of in A2? So what is f of 1 x1 x2? So f is x naught x0 square x1 square x minus x2 square. Yeah. So f of 1 x1 x2 is x1 square 1 plus, I shouldn't forget x0. So x0 is 1. Yeah. So it's 1 plus x1 square minus x2 square. Yeah, so we want this to be 0. So this to be 0 means x2 square minus x1 square equals 1. Yeah. So so it looks like a hyperbola if you consider x, if you ensure that x naught is sort of 1. So if you look at the affine open piece of P2, that affine open piece of P2 where x naught is non-zero, then it looks like a hyperbola. Yeah. If you plug in, so if you consider U1 intersection C, that means, so this is, by the way, C minus x naught not equal to 0. Yeah? So it's away from this. This is C minus x1 not equal to 0. That's what U1 intersection C is. X1 not equal to 0. So this is V of, so maybe I'll directly write down the equation. Yeah, so x1 is not equal to 0 means you set x1 equals 1. So this is V of x naught square minus plus 1 minus x1 square. Yeah. So this is also a hyperbola. So 0 locus of this guy. So here the local coordinates becomes x1 and x2 in A2. Here the local coordinate is little x0 and little x1. But again, it's a hyperbola in these two coordinates. Yeah? It's x0 square, x1 square minus x0 square equals 1. And if you consider the third one, x2 not equal to 0, this is u2 intersection C. Then this is v of the equation. So x2 is 1, so it's x0 square plus x1 square equals minus 1. V of this. So this is a circle. Yeah. So if you look at two affine pieces, you get a hyperbola. But if you look at this third affine piece, then you get a circle. Okay. So yeah, I wish I knew how to draw this, but yeah. So maybe from the cone picture it will sort of become clear. Yeah. So x0 equals x2 equals 1 means you do get a circle, something like that. Yeah. So that is one of the affine pieces. So x2 equals 1 means you are looking at the complement of x2 not x2 equals 0. Yeah. So you may have missed some points, but it's okay. X0 equals x0 not equals 0 means you can put x0 equals 1. Yeah, because you can just divide by x0. Yeah, and if you look at x0 equals 1, so it's something like this cross section, then you do see that you get a hyperbola. Yeah, something like this. So this I hope, so it's basically looking at cross sections of a cone via different planes. And somehow I remember I did this with you guys, probably in linear algebra. Yeah. And if you put x1 equals 1, then you again get this hyperbola. And I'm pretty sure if you take a particular cross section, you'll also get a parabola. But I don't remember which section you have to take. But anyway, that's so you see various pieces will give you so various open pieces will give you something something which is familiar. So in particular, it tells you that this hyperbola is sort of part of a circle as well. So if you take the intersection of these two open pieces, U1 intersection C and U2 intersection C, it's a big open piece, yeah. And so they agree. So hyperbola are so if you remove some points from a hyperbola, you can think of it as some subset of a circle. And similarly, if you remove some points from the circle, then you can think of it as hyperbola. So there are some, they are what is called birational. Okay. So in terms of algebraic geometry. Yeah. Okay, so this is, but anyway, I hope this homogenization and dehomogenization makes sense. Yes, so it's not homogenization, but this dehomogenization makes sense. So if you want to see how these projectives variety looks like in various affine, in these various affine open subset, then this is the operation you do. Yeah? So if I give you x in Pn, and you want to know how it looks like in this U0, this affine space U0, how it looks like in U1 and so on. You can do these various dehomogenization operation and see how the local equation in these affine patches look like. Okay. So projective variety, so projective space is made of affine spaces, and algebraic subsets in projective spaces are made of algebraic subsets in affine spaces. and we'll define projective varieties. So projective varieties is sort of made of affine varieties. Any questions so far? So I hope all this is making sense, but you should ask questions. I mean, of course, the lectures are online and you can view them all the time, but the point of all these lectures, live lectures, is that so that there is some sort of interaction. Yeah, and that is what will that will be one of the benefits of these lectures. Otherwise, there are a lot of lectures on algebraic geometry on the web. You can look at many of them. Yeah. Okay, so this was given an algebraic subset of Pn. You could look at various affine pieces and make sense of out of it, how it looks like in various affine pieces. Now we can do the other way as well. So if you are given some affine variety x in An, yeah, then you can consider it as you can extend it to whole of Pn. Yeah. Depending upon how you think of An in Pn, you'll get various extensions, different kinds of extensions. Yeah. So maybe, yeah. So maybe that I should have written here. So suppose X is in An is an algebraic subset defined by some ideal I. Then An you can think of it as so An you can think of it as in Pn in many ways. Yeah. So one of the ways is you think of An as U0. Okay. And so U0 is an element of is an open subset of Pn given by the fact that x0 is non-zero. Yeah, the homogeneous coordinate x0 is non-zero. Okay. So the construction I'm going to do is think of X as an open as an algebraic subset of U0 and then extend it to an algebraic subset of Pn. If you think of X as an algebraic subset of U1 instead of An, then you'll have to change wherever you have to interchange between a capital X0 and capital X1 in this construction, which I'm going to do. Yeah. So let IH, H for homogenization, be the ideal generated by x0 power d f x1 over x0 xn over x0, where f belongs to this ideal I. So I is the ideal is some ideal which defines x. Yeah. So you consider f x1 over x0, f xn over x0. So these are now these are sort of rational functions in x0 to xn, and let's say d is degree of f. Then if you multiply by x0 power d, then it doesn't remain a rational function. All the denominator gets cleared, and you get a polynomial in x0 to xn. Yeah. So you consider such polynomials. And this is going to be a homogeneous polynomial, right? Because, so is this okay that this is a homogeneous polynomial? Yeah, because you just check, yeah. So you multiply this by some, so you multiply each of these xi's by lambda. So assume k is an infinite field. And then, of course, you multiply each of these xi's by lambda. Then you get it's lambda power d times something. Yeah. So so this is a homogeneous polynomial, and you consider the ideal generated by such homogeneous polynomial. Yeah. So then, of course, IH is a homogeneous ideal, and V of IH is going to be some algebraic subset of Pn. And if you intersect it with U0, you will recover X. Yeah. So V of IH is the extension, is the so maybe um, V of IH is equal to the closure of X in Pn. Yeah. So X is if you think of X a subset of U0 which is contained in Pn, then you can ask what is the closure of X in Pn. Yeah, the smallest closed subset content. So so that is precisely V of IH. So let's yeah. So this should help in giving us yeah. So this should help in the other direction. So maybe the other direction. So for this statement where X is closed, X is Zariski closed in Pn implies X intersection Ui is closed. That we saw. Now, if X is some subset of Pn such that X intersection Ui is Zariski closed in Ui for all I between 0 and n implies X is Zariski closed in Pn. For that direction, you can use this. Yeah. So maybe I'll put that as a homework. That reverse direction. Okay. And what you'll need is this this particular statement. This maybe you can call it proposition. Yeah, so maybe we should remove this conversely proposition. So now we want to show that this V of IH is, so IH is clearly a homogeneous ideal, so that part doesn't require a proof. So we only have to show that V of IH intersection U0 is same as X. Yeah. So let's take some element in A0 to A, class of A0 to AN, an element of V of IH intersection U0. Yeah. So A0 to AN is, since it is in U0, A0 is non-zero. So this point is same as 1 A1 over A0 to AN over A0. Yeah, because you just multiply by A0, yeah, as we saw earlier. So this point belongs to V of IH intersection U0 precisely means that A0 is non-zero and f of A0 to AN is 0 for all homogeneous f in IH. Okay. So so now let f be such a so we want to show, what do we want to show? So we want to show that this so we want to show that this belongs to X. Yeah. So we want to show that A1 over A0 to AN over A0 belongs to X. Yeah, that is what our goal is. Right. So we will show that this vanishes for all f in I, and then we'll be done. Yeah. So let D equals degree of f, where f is in IH. Then f, since f is generated by these kind of polynomials, these kind of homogeneous polynomials where f belongs to I and D is degree of f. So f, capital F, we can write it as gi times x naught power di fi x1 over x naught to xn over x naught, where di is degree of fi. Maybe here itself I should have written fi is in I, and gi's are so since this part is already homogeneous, gi should also be homogeneous, so that the resultant thing is homogeneous, and homogeneous of degree d minus di, so that the total degree, so f has degree d, then each of these sums should have degree d. Yeah, each of these homogeneous pieces should have degree d, and this is a finite sum. Yeah. So this is what it means that f is an element of IH. Yeah. And so we'll come to the to what this this statement imply, but let's just analyze f. Yeah. So now you declare little f x1 to xn to be f capital F1 x1 to xn. So this is a polynomial in K x1 to xn. Okay. Then, so what I want to say is that little f actually belongs to I. Yeah. So that's what I want to. Maybe that direction is not needed for. Okay. But first we want to show that little f actually belongs to I. Um, um, this ideal I in kx1 to xn. Yeah. So little f x1 to xn is same as gi1 x1 to xn fi x1 to xn. Yeah, because you are just um, uh, because if you do x naught power d f x1 over x naught to xn over x naught, you will get capital F x naught to xn. Yeah. And if you plug in x naught equals 1 in capital F, then you get little f. So if you plug in in this expression 1, then you get this guy. And that tells you that, okay, so so that tells you that little f x1 to xn is in I, because small these fi's were in I. Yeah, so we got that this f is in I. Now this statement f f a naught to an is 0 for all f homogeneous in IH. What does that imply? That implies that a0 for d. So remember, um, f a naught to an is same as, if we write it in little f, in terms of little f, it is same as a0 power d f a1 over a0 to an over a0. Yeah, because of this fact. Yeah. Is this okay? So this is how homogenization and dehomogenization. So what we did, if you plug in 1, you get a polynomial which is not homogeneous, and then if you ensure that you divide by x1 over x naught and so on, and you replace little xi by xi over x naught and xn over x naught and multiply by x naught power d, where d was the degree of f, then you recover capital F. Yeah, so that is what we have done. Yeah. So this is 0 for all f homogeneous in IH, means this is 0 for all f in I. Yeah. And which implies, since a0 is non-zero, this f of this is 0 for all f in I. Yeah, which implies um, this a1 over a0 to an over a0 is in x. So this proves this inclusion, maybe. So this proves that V of IH intersection U0 is contained in X, and you can reverse this process. Yeah, so excuse me. If a1 is a1 over a0 to an over a0 belongs to Vi, which is belongs to Vi, which is same as X, then that is same as saying that this f of a1 over a0 to an over a0 is equal to 0 for all f in I. Yeah, and this is same as saying that a0 power d times. So now I'm starting with some arbitrary element here. Yeah, in X, and I want to show that a1 over a0 to an over a0 is in u0 intersection V of IH. Yeah, so we get that this is 0, so which is same as a0 power d times f of a1 over a0 to an over a0 equals 0 for all f in I. But this is a this will correspond to a where d is degree of f. Yeah, d is so d could be anything bigger than degree of f as well. So it doesn't matter. But let's say degree of f. Okay. Greater equal to. So for the reverse direction, you should take d to be degree of small f. Yeah, for the forward direction, yeah. So maybe the other direction ones. So maybe if I write d to be greater equal degree of f, then this is okay. Okay, and that will tell you f a0 to an is equal to 0 for all f homogeneous in IH. Okay, and that precisely means a0 to an belongs to v of IH, and since a0 is non-zero, it belongs to u0. So both sides are both directions are okay. Okay. So it's I mean, maybe it looks complicated, but it's not complicated. It's just homogenization and dehomogenization. So if you it's very formal. Yeah, you just write it down and see that it works out. So we have this correspondence, like in the affine case, algebraic subsets of Pn corresponds to, so if you look at, if we write down the ideal of definition of X, then we get, so we last time saw that we got a radical ideal. Yeah, so I of X is radical of I. So that was Hilbert-Nullstellan science. And of course, you given a radical homogeneous ideal in x naught to xn, you will get some algebraic subset. In fact, given any homogeneous ideal, you will get an algebraic subset. So there is a correspondence, yeah, between radical homogeneous ideals and algebraic subsets of Pn. Under this correspondence, irreducible algebraic subsets of Pn. So irreducible, the definition is same. You can't write it as union of two proper non-trivial closed subset, non-empty closed subsets. Yeah. So that is what. So the definition for irreducible affine algebraic subsets and irreducible projective algebraic subsets are same. Yeah. So we saw that irreducible algebraic subsets in affine space corresponds to prime ideals in the coordinate ring. Here you can, in this setup, you can show that irreducible algebraic subsets of Pn corresponds to homogeneous prime ideals in Kx not to Xn. Meaning, if you take the ideal of definition of irreducible algebraic subset of Pn, then you get a homogeneous prime ideal. And conversely, if you take a homogeneous prime ideal and take V of that or zero set of that, then you get an irreducible algebraic subset. So I'll leave that as a homework. Okay. For you to verify. And as I said, a projective variety is an algebraic irreducible algebraic set algebraic subset of Pn for some n. Yeah. So X is a projective variety. If you can think, you can realize it as irreducible algebraic subset of Pn. So so zero set of some prime ideal in homogeneous coordinate ring x naught kx naught to x. So a lot of parallel you can see, yeah, and that's about it. So there are many things which doesn't work. It's not completely parallel. But so, for instance, so one thing to remember, maybe I should say this, is that a projective, so affine varieties are more or less determined by its coordinate ring. Yeah, so if the two coordinate ring of two affine varieties are isomorphic, then the two varieties are isomorphic. But we haven't talked about morphisms between projective varieties. Yeah? But once we talk about it, we'll first define maps between so we'll define functions on projective varieties first. But when we define maps between varieties, then we'll see that two projective varieties may be isomorphic even if their coordinate rings, homogeneous coordinate ring, are not isomorphic. So, or in other words, given a projective variety, it can have many homogeneous coordinate rings depending upon how you try to embed it. Yeah. But that, so affine variety also you can try to embed it in various ways instead of embedding it. Say you are given a curve, you can try to embed it in A2 or A3 or so on, affine curve. But the coordinate ring is going to be isomorphic no matter which. There will be a ring isomorphism. But here it will matter. So if you embed it in P2, then you'll get some homogeneous coordinate ring. If you embed it in P3, you'll get some different homogeneous coordinate ring. And they may not be isomorphic as rings. So, but the variety is the same. Yeah, the projective variety may be same. So that is something which you should keep in mind. Okay, so let me define functions on projective variety. So x is some projective variety, and we want to define some functions on x. So, like in the affine case, what we did was we looked at elements of the coordinate ring and tried to define functions using those elements. So we can try to do that. So let's take f polynomial is homogeneous. So there we took arbitrary polynomial, but here we should take homogeneous polynomial because the right analog is to look at homogeneous polynomials. So if f is a homogeneous polynomial and a0 to n is a point in Pn, then if we try to evaluate it, f a0 to n, then it should be same as f of lambda a0 to lambda n, because a0 to n and lambda a0 to lambda n defines the same point in Pn. But we know that f of lambda a0 to lambda n is same as lambda power d f a0 to n. Yeah, for every lambda in non-zero in the field K, where d is the degree of this homogeneous polynomial f. So maybe this should be homogeneous. Okay. So this will be well defined only if d is 0. Yeah, then only you get this. So so this means that a homogeneous polynomial in Kx not to xn defines a function on x only if f is a homogeneous polynomial of degree 0. And such a polynomial is basically a constant. So any polynomial of degree 0 is a constant polynomial, and of course every constant is homogeneous. Yeah. So that tells you that if you look at functions in the homogeneous polynomial, if you want to define functions on x which are given by some sort of polynomial, and it should make sense on whole of x, then there are not too many. So there are only constants. Yeah. So that gives us some restriction on this projective varieties. Yeah, so there are not too many functions on projective varieties defined by polynomials in some sense. But in the affine setup, we also saw rational functions. So they were not defined on whole of x; they were defined on some open subset of x. So and of course, there are many more rational functions on affine varieties than regular functions. Yeah, every element of the function field is a rational function. Yeah? Whereas you have to take elements of the coordinate ring to write a regular function. So now we'll do something similar. We'll define a rational function, and then we'll see that there are interesting rational functions at least on Pn. So I'll take a little more time and wrap this up. Yeah. So a rational function on Pn by definition is f over g, where f and g are homogeneous polynomial of the same degree. Because what we want is if we just take f homogeneous and g homogeneous of different degree and we evaluate it on point, then we get So if f is of degree d and g is of degree e, then if you do this kind of calculation, which we did here, then you get f over g evaluated at a naught to n is lambda power d minus e. But if d and e are both same, then you get that it's well defined, no matter which representative you choose. Yeah. So that's why a rational function on Pn, we take it to be f over g, where fn in the function in the fraction field of kx naught to xn, where f and g are homogeneous of the same degree. Okay. So not every element of this function of this fraction field defines a rational function on Pn. Okay. But this yeah. So maybe note that f over g evaluated at a naught to an is does give you a function, yeah. A naught to an is basically you take f a naught to n over g a naught to n, and it doesn't matter which representative you choose. And this is well defined, as long as g does not vanish on a naught to n, defined on Pn minus the zero locus of g, yeah? Minus g equals 0. So since g is a homogeneous polynomial, g equals 0 is some algebraic subset of Pn. So the complement is an open subset. So this is open subset. So this does define a function on an open subset, and this is from an open subset to the base field k. Yeah. So both these will give you element of k, and hence it's an element of k. Okay, the ratio is an element of k. So similarly, if x is so this is how you define rational functions on Pn. And now we do the same thing like we did in affine variety case. Once you have so we know that polynomials define a function on an, and then we saw that if we restrict it to x, then it defines a function on x. And if you take appropriate regular function, then yeah, so if x is in Pn, be an algebraic set, then a rational function on x is a function defined on an open subset of x given by f over g, where f g are in k x naught to xn homogeneous of same degree. Okay. So this will be and here defined on an open subset. Let's call it U. Here U is basically x minus g equals 0. Yeah. So of course, if x is contained in the closed subset g equals 0, then this doesn't make sense. So so you also have to impose that of the same degree, and g is not identically 0 on or another way of writing it is g does not belong to I of x. G does not belong to ideal of definition of x. Yeah. So this is the definition. So maybe next time we will discuss more about rational functions. So maybe this is a good place to stop.